Hey, it's me, Steve. I'm going to do as quickly as I can I'm going to show you how to solve a geologic problem in the real world. Um, Geology isn't just looking at rocks and going ooh ah. It's you can actually use it to predict things. And this image is from Wetmore Landing last week when I visited, and that's the place where I'm going to start this from. Now here you see the Google Earth image. This is connecting two points. The bottom point, which will become point A, is from where that photo was taken at the beginning. And point B, up at the top, I've been there before. Then we're going to connect the two there because the Jacobsville group is exposed at both locations. And if you see here, you see the Little Presque Isle. I'm going to mention that again later, although it's not going to be taken into account while making this video. So here we have our point A and point B. We get the linear distance. We get about 5,100 feet. That tilt from due north is 13 degrees east. So I'm going to use that. And both outcrops, the bases are about 605 feet above mean sea level. We're going to need that for this too. Now, with this information, how do we calculate strike and dip the bottom of the Jacobsville group? Now, we're actually going to get a lot of information from this, and I'm going to solve this graphically. All right. I'm not going to solve it through using trigonometry. I could, but graphically, if you're efficient graphically and you do it to scale, you can actually see so much more. Just solving it through trig, it works and you get a more accurate and precise number, but you can't visually see what's going on. And if you have a geology protractor, you're going to be pretty accurate anyway. So I like solving things graphically, and I did that during the professional geology test. I solved everything graphically. I didn't use a calculator once, and I passed first time both tests. All right, so first, we'll assume that the distance from point A to B is the true dip of the rock. Strike and dip is consistent along our transit. That means it doesn't change. It's consistently what it's going to be. It isn't, but for this demonstration purpose, we'll say it is, and that comes back to the Presque Isle thing, because you can see the Little Presque Isle from the shore, and you can see the bed of the Jacobsville kind of dip towards you, which means southwest. And on the mainland, dips are kind of perpendicular to the basic outline of the coast. But for this purpose, we're just going to say it's consistent and everything is simple, for simplified purposes. At point A, the Jackson Formation is exposed in the cliffs at its entirety. The Jackson Oriented contact is at 705 feet above mean sea level. And we get that because we take the 605, which is the base of Jacobsville at point A, and add 100, we get 705 feet above mean sea level. The Jackson Formation at point A dips about 4 degrees. We got that measurement in the field. About 13 degrees to the northeast, and which saw that on Google Earth. At point B, we know the Oriental Formation of the Jacobsville group is exposed. So we know that formation is at the surface there. The Jackson Formation is not, which means it has to be underneath. Well, how do we know it's underneath? Well, you got to know the basic geology of the area that you're mapping or doing work in. And these units do exist at these locations. They just aren't. This is just a stylized representation. Like at the base, I put the Archean undivided. That's actually the Compo Creek gneiss. That squiggly line is an unconformity. The lines between the other units are contacts. Now, they're actually gradational in reality, but here we're just going to say they're solid contacts. And here are basic descriptions of the rest of the formations. The thicknesses are local thicknesses, assumed to be based on local data. The bottom Jackson Formation, honestly, is the only one we really know for sure from the field data as of yet. The other two should be about that. I just did this for demonstration purposes because I want to show you illustrate a point. And I put the Devil's Island sandstone there, even though it's not exposed along our transit, but is within the area. I just added that so you could get a total reference of everything that's exposed from bottom to top. All right. With this information, how do we calculate the strike and dip and the bottom of the Jacobsville group? Well, like I said before, we can solve this with trigonometry or graphically. Here I will solve it graphically. First, we need to set our horizontal and vertical scales, which for this example will be the same, thus simplifying the problem. You always want to do this to scale, because if you don't, you're going to increase your dip and get an apparent dip if you do any vertical exaggeration, thus negating this whole point. And why don't you just use trigonometry then? All right. So then now we can begin to construct our diagram. So we first draw, this is going to be a map view. We're going to go from map to cross section. But this is right now a map view, and that scale bar is 1,000 feet, that yellow bar, and that's going to be 1,000 feet no matter if we're in cross section or on map view. It's still going to be 1,000 feet. So we just draw a line that represents our due north. It doesn't matter how long it is, it just needs to be longer than that 5,100 feet. All right? So now we draw our angle that's 13 degrees to the northeast from our north. And as you can see here, I have two red 13 degrees. Those are complementary angles. They're the same. As throughout this, I'm going to switch from red when I'm talking about something, and then it'll turn white later. And then sometimes I might drop something off to make room so you can actually see what I'm doing. Otherwise, it's going to get a very busy diagram. So just keep that in mind. You can always go back if you need to. So here's our point A and B, and there's our 5,100 degree transit line. And this is constructed horizontal map view. So we have our horizontal now. All right, we're working on a plane here. Okay, and that red line is at 605 feet above mean sea level. All right, now we add our dip. Now we're going to go into cross section. Okay, so we add our dip. Since our dip follows that line, all we have to do is take our protractor, turn it to that to our line of transit, and tilt it to the right 4 degrees. That's all we have to do, and then we draw another line. Okay, so that is also that 4 degrees, since that was measured at the contact at the base of the Jacobsville. We know that red line right there is going to be our Archean Jacobsville contact throughout this whole thing, because we're assuming that everything here is planar and linear for illustration purposes. Now, since we know that dip is 4 degrees following our line of transit, all we do is take two 90-degree angles from our line of transit, and our strike is north 77 west. And as you can see in the upper right-hand corner, we'd write that north 77 west for northeast. All right. We don't need those lines really for anything else. I'm going to keep the bottom one. But, I mean, we don't need to know that from this point on. But they are going to come into play here. All right. So, what can we find out from this? Well, if we take 370 from 605, what's that 370? If you look at point B, the red line from the Archean to our 605 feet above mean sea level, if you measure that line, you get 370 feet, which would make it 235 feet above mean sea level. And if you look at our point A, right there, what we're doing is we are extending above. There's that red dash line. This red line is now a dash line. We are lifting that 100 feet above our 605 feet above mean sea level, so we can have the top of our Jackson Formation. All right. Okay, so now we take 270 from 605, we get the 335, which is the top of the Jackson Formation, and the base of the Oriental Formation is at 335 feet above mean sea level now. So at point B, so now we have the top of our Jackson at point B, and this is going to help us later, all right? Because I'm going to get into how you can use this information in practicality. All right, so there it is, just with all the red gone. So we've constructed this, okay? Now, why? Now, oh wait, before I get into that, okay, here we go. Now we can find along our line of transit, we can find any point and get the thickness to the Archean or to the top of the Jackson at any point. And here's point C. All right, we can physically measure this with our protractor too. We don't need to do any math. All these numbers, these feet and stuff, it's just gotten from direct measurements. All right, and here's D. That if we want to know the distance from point A along our transit line, where we will encounter the base of the Orienta Formation at 605 feet above mean sea level, we can predict how far we will have to travel to find that contact along our transit. In this case, it's at point D, 1,400 feet north of point A. All right, so you can kind of use that to predict where you would find this contact at the surface. Okay, and hopefully when you physically get there, it'll be exposed, but sometimes it isn't. All right. So now if we need the elevation to the top of the Archean at point D, we can get that as well. We just take the 110 feet, which is that red line. It's kind of hard to see, but there is a line there. That's a physical measurement on our graph here. We take that from the 605 and we get the top of the Archean will be at 495 feet above mean sea level. All right. Why is any of this relevant to anything? Okay, so I just ran through you graphically how you can figure stuff out like this. Well, we can use this information to generate cross-sections on a geologic map. I do this all the time. Now, geologic maps aren't that simple. Geologic units are not planar throughout your map area. You have things like faults, you have folds, you have things like that that mess with it. But in this example, we could use that to actually just do our cross-section. And I do plan on mapping this area in detail and that Little Presque Isle eventually. I couldn't do it. We went to go to Little Presque Isle this past weekend and the waves were too high. But if we had been there the day before, we could have done it. But, you know, that's neither here nor there. And now we're going to have to wait till May. So like 7 months. But anyway. So you can use it to generate a cross-section on a geologic map. Well, who cares? Well, because geologic maps can be used for other things. And you can use this for other things. Like we can use our predicted elevations to explore for resources. Say there is a copper deposit known at the base of the Jackson Formation on top of the Archean. And we want to drill at point B. We can't drill at point A, but we want to drill at point B, or there's no copper at point A. So now we have that data, that predicted data I just showed you. We can guess where we're going to hit the copper. So we can set up our drill rig. We can get everything going. We can get what we need without spending exorbitant amounts of money. When people drill for things, looking for mineral resources, they never go in there blind. Those days are over. That's 19th century stuff when we didn't know really how geology worked. Now we know. So you can actually use that to predict something. Or say we wanted to get groundwater, say the top of groundwater was at the top of the, it was at the top of the Jackson Formation and the base of the Orienta. Anywhere along that transit line, we can find out and predict how far we have to drill to get that groundwater. So you see, this stuff has practical applications. It's not just all, oh, that's cool. I mean, and if you generate a geologic map, you can generate cross-sections from that to predict other things as well. Yes, it has academic value. Yes, it's important to figure out the history of the planet, but you can actually use this to find stuff. All right, and this final picture here, before I let you go, is just my quick drawing I started to do by hand before I decided to do this for you and share it with you all. But anyway, that is it, and I hope you learned something.